Hi, everyone. Thank you so much for joining. Today, we will be talking about anomaly detection. So, the goal of this video is to give you a high level understanding of what anomaly detection is, how to use it, as well as some tips and tricks along the way. By the end of this video, you should be prepared to start your first anomaly detection model. So first off, what is anomaly detection? Anomaly detection is a built-in Snowflake ML model which allows you to identify outliers in time series data. It's particularly useful to pinpoint any abnormalities or deviations in your dataset. An example of this would be if you're looking at account usage data over time and you want to see any anomalies with cost or security. The only two requirements to use anomaly detection are that your data must include a timestamp column and a target column. You can also use anomaly detection for single series or multi-series data. Now let's dive a bit deeper into some of the key features and capabilities. So first off, anomaly detection can be created as a supervised or unsupervised model. Let's say you're initially working with an unsupervised model where there's no label data set, but you're not quite getting the accuracy that you'd like to see. Sometimes by having a label data set and doing supervised learning can actually help boost accuracy. In the built-in anomaly detection function, you can actually create an additional Boolean column where you would label each value as anomalous or non-anomalous, and that would allow for supervised learning. By having this flexibility between unsupervised and supervised, you can customize your model a bit better. Additionally, anomaly detection can include categorical or numerical variables. Essentially, if you have data which may influence the target variable, you can include that in your model and have some flexibility on the data type. Lastly, since anomaly detection does not rely on one-hot encoding, you can use variables with high dimensionality. Anomaly detection also allows you to have some flexibility with single series or multi-series models. A single series model allows you to analyze time series data that is coming from a single source. For example, if you're looking to compare the total sales for a business over several days, you can use a single series model. Essentially, since there's only one business with data over time, this would then be considered a single series model. On the other hand, a multi-series model extends the same concept. However, it is using multiple related time series data. So, an example of this would be if you have that same store but with several products, and you're interested in seeing how each product at that store contributed to sales over time. The only difference is that you would put multiple columns together to identify the series. Now that we've talked about some of the key features, let's go over what's happening behind the scenes in the backend. So, the Snowflake built-in anomaly detection function uses a type of machine learning model called gradient boosting machine, which is an ensemble method that combines multiple weak learners to create a strong predictive model. It can handle trends in the data and also use past values to predict the future. The algorithm also uses rolling averages, so it looks at the average value from recent past data to spot trends, and it also figures out calendar information to help with predictions. After the model is ran, you'll receive a prediction interval, which includes a lower bound and an upper bound where we would expect the data to fall. If the data is not within that range, it is considered an anomaly. You can also custom specify the interval. So right now, the default is 0.99, which means that 99% of the data should fall into the range that we're providing. However, you can always change that around to like 0.95, zero point 0.9, depending on what your needs are. Now we'll discuss some of the limitations. The anomaly detection function works best for straightforward use cases that require minimal customization due to some of the limitations that we have. So, some of the limitations are that the anomaly detection model is fixed, which means you can't really tune for trend, seasonality, or amplitude. It's just something that's given or figured out in the data. Additionally, you must have at least 12 data points per time series model for a full detection. The timestamps must be at least 1 second apart, and the minimal seasonal granularity is 1 minute. The season length for autoregressive features is tied to the input frequency, and also models cannot be updated or versioned. So every time you want to create a model, you have to create a new model, and you can't go back to previous versions. So that's just something to keep in mind. And lastly, models cannot be cloned. Now let's get started with our demo. So for the purpose of the demo, I've selected a data set, which is a COVID-19 sample, and this is specific to the state of Minnesota. So here, all we're looking at is the n- timestamp, the negative new results reported, the negative total results reported after each day, positive new results reported after each day, as well as the positive total results. So, first, once you have your set, what you're going to do is split that up into a training data set and a test data set. So, I did that really quickly. And the one thing you actually want to make sure of when you're doing this is have it ordered by the timestamp and make sure that every data point in your test set is after every data point in your training set. So you need to make sure that none of the dates are overlapping and it's in different time frames. Once you've created your training and test set, you can first create the model. So here's the function that you would do to create that model. So first you have the actual anomaly detection model that we're calling, and then you can name it, whatever makes sense for your model. There's a number of inputs that you can include, but for the purpose of today's demo, we've kept it pretty simple. You'll use your training data set as the input data. So this is just how I call in the view. You need to provide the timestamp column and the target column. So these are the two that are mandatory. And then for the label column, we don't have a label. Yeah, so here you're going to call the anomaly detection model. So we've kept it pretty simple here, just included all of the same values as we did when we were creating the model. The only difference is I wanted to change the prediction interval. So as I mentioned previously, when we have the default, it's 0.99, but here I've set it to 0.95. So that means that 95% of the data should be contained within the lower bound and the upper bound. Once you call the model, this is kind of what you get. So your timestamp, what the forecasted value is for that row. You get the lower bound and the upper bound. So in this case, for the ones that aren't anomalies, you'll see that the forecast is kind of within the bounds. In the case that it was outside the bounds, we would see that as an anomaly. This was just a quick and easy demo for anomaly detection. Hopefully, this was useful.